Great, yeah. So my name is Lawrence Peirson. I'm a graduate student at Stanford with Roger Romani, and I'm going to talk about X-ray polarimetry, which is quickly going from a technology of the future to one of the present. And in this talk, I'll explain some of the work I've done to extract the maximum possible signal from these instruments. And rather than describing any specific hardware for any instruments, I'm going to talk about data analysis techniques that should be general to any imaging X-ray polarimeter, and hopefully other instruments as well. So from a data analysis perspective, X-ray polarimetry is actually a really rich and challenging problem. Individual X-ray photons come into the detector and produce these photoelectron tracks. And from each of these individual events, we need to extract the photoelectron angle theta, so the initial direction the photoelectron went, which is shown by the green line on the plot there, the coordinates of where the X-ray interacted on the grid, if the polarimeter has source imaging capabilities, and also the energy of the event. And then we have to do this for a large group of events. And then because the photoelectron angle follows a known distribution, a cos squared theta distribution for a polarized source, we then need to extract the polarization parameters from a big group of events shown in this histogram here. And so this whole process can be broken up into two main steps. The first being extracting the parameters from individual events. And the second is taking a big group of these events and extracting the polarization parameters. And I'll explain contributions we've made to improve both steps individually and how we managed to combine both these steps into one to get optimal signal to noise in this problem. So the first step, estimating individual event parameters. Previous methods and the sort of standard methods use weighted track moments to estimate the photoelectron angle and also the absorption point. And they use a linear function of total charge deposited to get the energy. So pretty simple, but it works quite well. Our method, we use convolutional neural networks trained on simulated events. And convolutional neural networks are sort of state of the art in image analysis. So this seemed like the perfect problem to apply them. Now, when working with non-square grids like this hexagonal one here, there's a few important things to mention about that. Since neural networks are linear algebra machines, you need to make the images into square matrix form. But if you do this naively, you actually introduce a lot of biases into the final polarization parameters that you estimate, the step 2 part I mentioned in the previous slide. So you need to be a bit clever about doing this. And previous neural network approaches for this problem, and also things like CTA, have actually struggled with this hexagonal to square conversion. And we came up with quite a nice simple solution to this, which is instead of converting the hexagonal whatever grid image to a square one just once, we transform it all 6 possible times with pixel shifts, and then give these all to the neural network and re-rotate the results back at the end and average them. And this really simple method actually eliminates any polarization biases at the end. Now, in step 2, we have a big group of tracks that we've estimated the angles for, and now we want to estimate polarization parameters. And there's a lot of things we could do here. You could fit the histogram bins, or you could use maximum likelihood estimation. But it turns out really the best method is to work in the Stokes parameter frame. If you transform to Stokes parameters and then just estimate those, this has all the nice properties of a maximum likelihood estimation, but without any of the hassle. So this is a really nice method. And I could stop the talk here and say, okay, we applied neural networks and we got state-of-the-art results, great. But we can actually do a lot better than what I've said so far. And the trick to doing better is noticing that individual events, the track morphology for individual events varies widely. It depends on lots of things, but even at the same energy, tracks look super, super different. And that means that our estimates for the photoelectron angle theta, the direction, have really varied uncertainties between events. Some are estimated really well, some are estimated really poorly. So in this kind of situation, a weighted analysis can really improve your signal recovery. And it turns out that the Stokes parameter estimation approach can be really easily modified to include individual event weights. And so this is great, but now the question is, what weights do we use? And unpacking that a bit more, it's how do we quantify the uncertainty on individual events, on our predictions? And secondly, how do we then turn those uncertainties into weights that we can use that will optimize the signal to noise ratio? So the first part, we want to quantify the uncertainty on each of our predictions for each individual event. And you can actually do this with a really nice technique from machine learning called deep ensembles. So in a standard neural network approach, the network is trained to minimize the mean squared error on the predictions. So this is just the standard way of doing it. But in a deep ensemble approach, what you do is you minimize a negative log likelihood of a Gaussian, and you're not only predicting the angle theta hat in this case, but you're also predicting the standard deviation on your estimate. So in this way, you're actually training the network to predict its own uncertainty on its predictions. And this actually works really well. So I would recommend this approach to anyone who's using machine learning for uncertainty estimation. But it turns out for our problem, since the photoelectron angles are periodic, we tested out a von Mises distribution instead of a Gaussian. And this actually works much, much better and provides better results. So what we're actually doing is minimizing the log likelihood of a von Mises distribution, which is just the Gaussian on a circle, really. And our network is predicting not only the photoelectron direction, but also this von Mises concentration parameter, which is basically the same as 1 over the variance for the Gaussian case. So this kappa parameter is quantifying our uncertainty on that individual event angle prediction. And now we want to translate these individual event uncertainties into weights that we can use when we're estimating the polarization parameters. So it's not really obvious at first how to do this best, but we actually proved that the best weight to use for any individual event is its expected instrument response, or its expected modulation factor. That's the language of X-ray polarimetry. So usually the instrument response is something that you can only measure for a big group of tracks, because what we're measuring is polarization. So, and you need a lot of individual events to measure that. So before this work, there wasn't really any way to get an individual instrument response for an event, which we know now provides the optimal weight. But with a little error propagation, we were actually able to do this. And so, you know, assuming our neural network estimates are unbiased, and we have this sort of von Mises distribution for the error, we can actually work out the function that transforms the kappa parameter that we predicted with the neural networks, our uncertainty prediction, into the expected instrument response for that individual event. And by doing this, we're actually getting an optimal weight for that event. And so these are the results here. On the left, I'm just showing the modulation factor, which is the instrument response, as a function of event weight. And the red is our optimal approach here. And you can see, you know, each of these points is like 20,000 tracks or something like this. And the different kinds of points are 2 different spectra. So the red line is showing that we're, with our approach, recovering optimal weights. We should lie on the y equals x line, and we're very close to it, almost on top. And we're also completely spectrally dependent, which is also what you expect from optimal weights, because they should be universal. And then on the right at this table, this is showing the minimum detectable polarization for some of the different methods. And this weighted approach with the neural networks that we're using is reducing the minimum detectable polarization from the standard moment analysis by 25%, which ends up being a reduction in exposure times of more than 40%. So this is really an enormous improvement to get from just changing up your data analysis pipeline. And the nice thing about these weights is, they're kind of universal. You can do it for any spectrum. You don't need to worry about any tuning or anything like this. It's really easy.
5 minutes, Peirson.
Yep, thank you. And well, so this is my final slide. Yeah, so just to summarize, we've derived and applied an optimal weighting scheme here. And under certain assumptions, like, your neural network estimates are unbiased, and you have a von Mises distribution, which by the central limit theorem is pretty reasonable, and we've confirmed it is reasonable. Then we have the optimal analysis here. You can't actually really do better. And we've actually, applied this to real detector data, not just simulated data, and it works really well. All the results that I've shown kind of are recovered on real data too. Although there are some interesting effects with real data that are specific to instruments that I don't really have time to talk about, but it all ends up working out. So that's quite nice. And we're working together with XP to make this one of the standard pipelines. So thanks for your attention, and yeah, I'm happy to take questions if there's time.